Thank you so much for the kind introduction, Raphael, and thank you all for being here in person or online. It's always really great to see faces, and as a government employee, we never have food at our meetings. It's so heartening to see all this. So as was sort of alluded to in this introduction, my research goes into kind of the methodologic side of occupational studies and environmental studies. In particular, today I'll talk about healthy worker survivor bias, but I also do work in exposure mixtures. Contrary to my position at the National Cancer Institute, not all of my research goes into cancer outcomes. So I've done a lot in reproductive health as well. But given my hire at the National Cancer Institute, my research has been more focused recently on cancer. The unifying principle in all the work I do is the sort of modern understanding of causal inference. So I put a DAG up on this first title slide just to reference the fact that a lot of what I'll talk about is causal inference, and not causal inference as we've understood it over thousands of years, but causal inference in terms of the somewhat limited framework of potential outcomes in causal inference, which has been really speared from work by Donald Rubin, Jamie Robbins, and sort of more recently, and the way to popularize this, Miguel Hernan. So if you're a little bit uncomfortable with this framework, some of this will be baby steps through this, but underlying all of this really is the idea that we can learn more about data than we used to, given our understanding of causal inference. So today I'll just talk a little bit about history of healthy worker survivor bias. You may have heard of it as the healthy worker survivor effect, or even just healthy worker effects. I'll go into theory using causal diagrams. And when I say theory, I don't mean theory to put any of you to sleep, but just sort of introducing you to how we've modernized our understanding of biases in occupational studies that's given us a set of tools to address those biases, at least in some circumstances. And so I'll talk through the circumstances where we do feel like we can make progress in doing analytic adjustments if we can't do anything on the study design side. This talk was originally a webinar for EPICOH, which if you're not familiar with, it's just a bunch of occupational epidemiologists who pay some money to talk to each other. But the workshop actually was sort of oriented towards teaching, and there's a worked example that's on a GitHub site here. If you're into that sort of thing, you can do that, and kind of the end of the talk that I'll be very brief about is going through a worked example, just to give people some idea of what it would actually take to address some of these biases analytically. So in terms of what humans have understood about occupation and biases when looking at occupation and health, mortality has long been observed to be lower among populations of active workers. So the sort of written record on this, I think would go back to Paracelsus, but in terms of sort of healthy workers survivor biases, where workers who are healthier sort of at baseline just persist in the workforce longer. Our written record of that goes back at least until William Ogle in 1885 in an annual report to the Registrar General of Births, Deaths, and Marriages in England. And so this sort of phenomenon has been understood in a lot of time, and Ogle writes that industries, particularly industries that take a lot of what he would describe as vigor, carried on a body of comparatively picked men at that time, stronger in the beginning, so workers who are healthier get selected into an industry, and maintained at a high level by the continual drafting out of those strength who falls below the mark. So this is really the first sort of precise description of healthy worker survivor bias, and I think what keeps a lot of us up at night to this day is that it's not. This is just sort of a function of occupational studies where a lot of the things we look at, it takes some baseline level of health to stay employed, which turns out to be problematic. Nothing was really attempted analytically to deal with this sort of phenomenon. It was just sort of noted and left alone, and maybe people did sort of internal checks like, okay, mortality is below the standard mortality here. I'm just sort of going to mentally bump that up. But really the sort of methodologic efforts at addressing healthy worker biases started in the 1970s with this seminal paper by Fox and Collier. What they described as the survivor population effect was they sort of broke this down by stratifying SMRs by tenure in the workforce. And it's not worth getting too much into their methods because we don't do this too much anymore, but they noted that the SMR for past workers, so workers who had been in the workforce but were no longer there, including retired workers, was over sort of this null value of 108. So these workers who had left the industry experienced higher mortality than the general population, while those who are still in the industry had an SMR of 74. Again, this null is 100. So workers who were still in the industry experienced much lower rates of mortality while they were on the job. A more modern understanding of this in terms of regression models or exposure response curves, I think is illustrated nicely here. You've probably seen a lot of examples of this, but I really like this particular example from 2013 by Bjordal, who looked at a cohort of 13,000 iron miners. And so they stratified by the employment time in this cohort by whether or not you were an underground miner or whether or not you worked at the mines but were not underground. So the idea here is that if you're an underground miner, it's a much higher exposure scenario. You are expected to be at a much higher level of health versus people who are working at the surface that may include some administrative workers or just people who, for whatever reason, can't work underground. And so what you see here is in expectation with rectal cancer and the exposures of iron miners, which is going to potentially include a lot of things, you would not expect that iron mining work would necessarily be beneficial. There may be some benefit of getting exercise, but sort of taking all the exposures in total together, you would not expect working as an iron miner to be beneficial for rectal cancer. But in fact, what these investigators saw was that for duration of employment, you saw this inverse exposure response relationship. And I think this is highly characteristic of healthy worker survivor biases, where the longer you've been in the workforce or the higher your cumulative exposures are. If those exposures are not extremely, extremely, extremely toxic, you can see these inverse relationships where high exposures or long duration of employment appears to be beneficial for health, even though that goes against all experimental and other sorts of evidences that we see. So this is sort of the concern that warrants like a deeper dive into healthy worker survivor bias as something we need to correct, because when it happens like this, it's fairly obvious. We don't think that working as an iron miner is beneficial in terms of rectal cancer. But thinking about those miners who are above ground, workers who are above ground, there's something a little more nefarious here, which is, this is something there's an exposure response that's statistically compatible with a null. There's this downward bias that we see, and it doesn't look so inverse that we would think, oh, this is obviously bias. But what this shows is that this bias is always there, regardless of whether or not we see something inverse. So if we observe an exposure response in the direction that we expect, generally with healthy worker survivor biases, it's also going to be an underestimate. So even when we detect something, if we use our estimates from these occupational cohort studies to make decisions about worker health, ultimately we're failing in terms of worker health because we are potentially grossly underestimating the effects of workplace exposures. An example from my work in a different setting involves this cohort of 8,000 copper smelter workers from Anaconda, Montana, which is near where I grew up. Actually attended a wedding in Anaconda, and when I was driving through, this copper smelter has been shut down for a long time, but driving into town, there's maybe a 2 or 3 mile stretch where on the side of the road, there's this big slag heap. So it's just this black slag from the copper smelter that's been there, since the early 1900s, and it's just sitting right outside this town. There's been no remediation, for at least 50 years on this huge slag pile, and it's just miles and miles, and it's, I'm going to say 100 feet tall. At least it looks that way from the roadway. So these are potentially like really highly exposed workers, but just keep in mind this is a context of a very highly exposed town of individuals as well. And this cohort was originally put together by Joe Framini, who was instrumental in the formation of the National Cancer Institute. And in an analysis with Jay Lubin, who's still at the National Cancer Institute, they found no significant trends in the relative risks with various measures of cumulative arsenic exposure. However, they did find some evidence that cardiovascular disease in these workers caused retirement. So in doing this analysis, they sort of said that there's really no evidence of an effect of arsenic exposure on cardiovascular disease. And here I should emphasize, there's plenty of evidence at this time, even when this paper was published, that there is an association between arsenic and cardiovascular disease. What they were looking at specifically was arsenic trioxide in terms of an inhaled exposure. So there was still some debate about whether that exposure route was leading to poor cardiovascular outcomes. And their take on this was that there really isn't evidence for that. In a response to this particular paper, Urs Hertz-Pichetto and Henry Rigi, who was the senior author on this, described the evidence that they saw in the Lubin and Framini analysis a little bit differently. So in this description that cardiovascular disease potentially causes the retirement, they call this an excellent description of how the healthy worker survivor effect operates. So we know, based on sort of historical evidence at least, that workers, folks who are able to maintain, staying at work, generally are healthier than the general population and healthier than the workers who leave work. But here they're making a direct statement about the effect of a particular disease on leaving work. So this gives us sort of a mechanism behind how that happens. Workers develop cardiovascular disease and then they leave. And potentially, if cardiovascular disease is caused by the exposure at work, you have some interesting things that come up. And this is what leads into sort of our modern understanding of causal inference. Just a brief kind of rejoinder to this. In one of the papers that I worked on as a graduate student, I did a reanalysis of this cohort using one of these modern causal inference methods that addresses healthy worker survivor bias with my advisor at the time, David Richardson. And we found actually an excess of deaths from heart disease. We just sort of redefined the Lubin and Framini definition of cardiovascular disease, but found an excess of the absolute risk of heart disease. There was as high as 18 workers per thousand. So 18 excess deaths from heart disease by age 60 among these workers. So this is something where we have, I think fairly compelling evidence that actually arsenic trioxide is associated with cardiovascular disease mortality, using the same data that Lubin and Framini said. In fact, there is not evidence. The real difference between these was we updated the methods by which we did the data analysis. So my take on this, as a methodologist, is that to address healthy worker survivor bias, I think methods always matter. There are things that you can do with study design about a lot of epidemiologic biases, but this is one setting in which study design can't necessarily get you there. There's nothing you can do to force sicker workers to stay in the workforce. And because these are observational cohorts, you don't have experimental control over a lot of things. And what this manifests is something that we discuss a lot of times in occupational or any observational studies, which is this is just an example of confounding. It's something we can't fix in our occupational cohorts. And if we're using occupational cohorts to make decisions about worker health or to make decisions about the population health as a function of the workplace exposures that may be in the environment. This is something that we just have to deal with in an analytic way, and we can't deal with it on the study design way. So the terminology note, I use the term healthy worker survivor bias rather than healthy worker survivor effect. You could maybe say there's a distinction here with no difference, but I use this terminology because this is a structural bias of specific parameters that is amenable to control via some methods, rather than a singular effect. So what I'm going to try to do is to describe this in a very precise way, where it gives us a way to control a bias rather than just sort of this nebulous effect that's always there. And I will say you can't always control it, but at the very least, naming it and describing it makes it a little less scary to me. So to sharpen this distinction, it's helpful to see the structure. And this is where I think the theory of healthy worker survivor bias, in terms of being an issue of structure rather than something sort of nebulous, is very helpful. So when I use the term structural here, I say healthy worker survivor bias is a structural problem. The word structural is kind of lifted out of the causal inference literature. And what that really means is this relates to causal effects that we see. So this is a DAG here, if you're not familiar with these. And if you draw an arrow between two things, that means U causes L. So with healthy worker survivor bias and DAGs in general, we usually use the letter U to denote something that is unmeasured. So this is always the concern in occupational studies, that we've got things that are unmeasured that we just can't adjust for. Those things we think are ultimately determinants of health outcomes. So in the copper smelter analysis, this would have been cardiovascular disease mortality as an example of our outcome. In healthy worker survivor bias, we are also concerned specifically about employment. So duration of employment is one of those things that predicts health. The longer you've been employed, generally the healthier you are. That's not necessarily a direct causal effect of maintaining employment on the health outcome. It may be something like, if you're employed, you have health insurance that is going to help you with some health outcomes that you're interested in. But I think that the broader concern sort of is that the relationship between employment and health really comes down to what we would kind of classically call the confounding fork. So we have this unmeasured health status that determines whether or not you're going to stay at work, but it also determines your health outcomes. And the other particular thing about a lot of what we study is that employment determines whether or not you're exposed. In some cases, this is absolute. In some cases, it's a matter of degree. But for most of the things that we study, the reason why we study them in occupational populations is because there's something about being at work that leads you to be exposed to the things that we're interested in. So, for me, this was copper smelting and arsenic exposure. The workers who were exposed, or the individuals in Anaconda who were exposed the highest, were ultimately individuals who are still working at the copper smelter. So described this already a little bit. The thing where DAGs become useful if you haven't been steeped in this literature is it gives us a very fine and precise definition of epidemiologic confounding. So it gives us hope that we can identify things that we can control for in our studies, things that we can measure ahead of time, by which we can control this bias. So in this case, sort of the question that I would ask of students is U a confounder of the association between the exposure and the outcome in this situation? I won't turn this into a Socratic thing. I will just say, yes, U is a confounder. And the way that we understand this from the causal inference perspective is that there's this pathway from exposure to the outcome that it's not this direct causal effect, but it's what we would call a backdoor path. And so we would define U as a confounder. The other question is whether or not employment status, in this case, would be a confounder. So if you're at work, or not at work? Is that something that we can consider a confounder in this study? And the answer here is yes, L is also a confounder. And then the final question that I always ask students with this is there confounding by U after we adjust for L? So if we do something like go into an occupational cohort study, we estimate an effective cumulative exposure on cardiovascular disease mortality, and then we adjust for employment status. Is there still confounding by unmeasured indicators of health? In this very simple DAG, there is not. And this is what gives us the key to solving this bias analytically, is that when we can identify things that are kind of upstream or downstream, depending on where you are in the stream, upstream of this health status, things that we think determine your mortality and employment, if we can identify a series of things to adjust for, then we can address healthy worker survivor bias. So here's this very simple diagram of employment status, but this could be something like, it could be where you're working at in a mine. That could be something like if you're a very robust miner, it may be that you are put into the most highly exposed areas of the mine. And so because of that, you would have sort of this other pathway where your health status determines your job title determines your exposure, and now we have something other than employment. Today I'll speak mostly just about employment, but just want to emphasize this gives us the tools for thinking about what we should be measuring on in occupational studies in order to address this bias. So the answer, yes, no. And the conclusion, if we can adjust for L, we do not need to measure U. And I think this is sort of the remarkable thing that we learned from methods, is that our concern is always this unmeasured health status, but we now have a tool to address bias for these unmeasured things, given that we know something about the scenario. So going a little bit more deeply into this, into theory, with healthy worker survivor bias, this isn't just a matter of, are you employed at baseline, and then we look at you for the rest of your follow-up time. Healthy worker survivor bias really is a phenomenon of things that are dynamic over time. So if you're at work in year 1, that doesn't mean you're at work in year 5, but whether or not you're at work in year 5 is going to be a strong determinant of your ultimate cumulative exposure by the time you reach a certain age or you reach a certain tenure at work. So the way that we denote this with DAGs is by indexing things by time, or T here. So in the world of DAGs, we work at discrete time, so we would say time T or time T minus 1 are two distinct time points that we look at. In the work that I do, I often separate my data out into person years. So you could think of this as exposure in 1 person year, and then this is exposure in the prior person year. But the introduction here of time really doesn't complicate the DAG a whole lot, and so it doesn't really complicate our understanding of healthy worker survivor bias, but for the fact that we have now exposure being involved in this dynamic process in the workplace. And so I'll get into what this means. So based on the previous slide, employment status is a confounder, so we think we should adjust for that. And if we have a structure like this where employment status, we know that it determines exposure over time, so whether or not you're showing up on the job site, whether or not you've shown up at the World Trade Center on day 1 or day 3, that's going to strongly determine the exposures that we have for you. And so we just sort of assume this at all times in occupational studies, that if we had some measure of employment status, or other things like where you're working at on the job site, those give us hope for addressing confounding. And even if it's dynamic over time, all you need to do is adjust for employment status for those things. The complication arises here if you have exposure determining whether or not you stay on the job. So one of the things with the copper smelter study was that cardiovascular disease leads to people leaving employment. If arsenic is a cause of cardiovascular disease, by sort of extension, arsenic would then be a cause of leaving employment. And this is where the real complication arises. This is where the usual methods for data analysis and epidemiology fail us. In the terminology of DAGs, L is what's known as a collider. And I'll just talk you through this a little bit. But it's an interesting topic. It's a little bit hard to grasp. But the idea here is with every DAG, there's a flow of information. So information flows along these paths, meaning we have, given that we know Y, we know something about X, or given that we know exposure, we know something about your outcome. Given that we know that you're exposed, we know you're probably at work at a given time. Given that you're at work, we know something about your health status. And given that you're at work, we also know something about your eventual risk. However, when you have a collider, what this relationship says is that actually, given your exposure, we don't know anything about your health status. And if we knew something about your health status, it wouldn't tell us anything about your exposure. With the one caveat that if you stratify on are you at work or are you not at work, that makes information flow along this particular path. So a collider is a problem because when you adjust for it, when you stratify it, now all of a sudden you create an information flow. And this creates something like additional confounding. So employment status in this case is a collider. We shouldn't adjust for it because it actually induces a bias in our study. And something to note with most occupational studies that I've ever been involved in, we're often interested in cumulative exposure. It's not just exposure at one time point. We want to know how much you've been exposed to during the tenure of your work and what kind of effects that has. So, effects add up over time. And our way of sort of getting to that is by having metrics like cumulative exposure. So because we are interested in cumulative exposure, because employment status is a collider, and because it's a confounder, we have something that's called a confounder that's affected by prior exposure. So this is sort of the structural problem that launched 10,000 causal inference articles. This was the exact problem that Jamie Robbins was trying to solve in 1986 that led to what was eventually marginal structural models and completely changed the way that epidemiology is done, at least in terms of HIV research, in terms of pharmacoepidemiologic research, and some of this is still percolating through. So this idea that we can have confounders that are also affected by exposure sort of breaks our usual tools. We can't just fit a Cox model and adjust for employment status in an occupational study because we induce extra bias. So we can think of healthy worker survivor bias now in terms of something that is maybe still scary, but it's something we can address using some of these methods for causal inference that have been adapted for this exact situation. We think of often as confounding by employment status, and because employment status may actually be affected by exposure, with healthy worker survivor bias, we think of this as just another example of confounding where the confounder is affected by prior exposure. Just a brief foray into this, because I think this is often of interest. If we don't have direct measures of exposure, so this would be something like you have a workplace and you want to estimate SMRs because you know the workers are exposed to something. You may not know exactly what it is, or you may not be able to measure it. Oftentimes, the thing we do is instead look at effects of being a member of that cohort itself. So we do things like take an SMR, comparing the mortality rates in an occupational population versus general population. The way that we think about this is just sort of using L as our exposure. Here we have the same problem. So when you have an SMR study and you get SMRs that are below the null of 1, oftentimes it's this same structure where we have some association between unmeasured health status and being in the workforce that's associated with our outcome, and that leads to confounding that we can't necessarily deal with. So employment there is just really a proxy for exposure. And so the problem really doesn't go away when you're thinking of employment as your exposure itself. And I'll just say that SMRs below 1 are the rule rather than the exception. I don't want to get too deep into this, but this is just to say these two concepts are highly linked. And so we might think of methods that deal with them in the same way. So just as a summary of healthy worker survivor biases, I think both healthy worker survivor bias and healthy hire bias, both of these are biases we'd like to control. That's sort of the ultimate goal when thinking about estimating impacts on workers. In healthy worker survivor bias, though, we have this introduction of collider stratification bias. This is the bias we want to avoid, but we can't through usual methods. And really this relies on our interest in cumulative exposure. But this problem sort of persists, if we're thinking about just comparing occupational populations with the general population. So I'll get a little bit into methods, and I'm gonna give just sort of a brief overview of what is done. I'm gonna skip broadly over kind of the worked example, but just want to raise this idea of methods. So with healthy hire bias, if this is a concern, we have actually some methods from causal inference recently that have become useful for addressing, you've done SMRs and you get all your SMRs are below 1, and then you're like, what do I do? One of those things is to find a worker population. Occupational epidemiologists have done this for a long time, but in sort of the modern parlance, we call that finding a negative control exposure, where we find sort of another occupational population that's subject to like the same sort of health selection. So we have the same associations between you and employment and you and the outcome. And we use that as a way to kind of subtract out the effect of confounding there. We also have this tool called negative control outcomes. And that can come if we have an outcome that we generally identify as being completely immune to the exposure, or exposure at the workplace cannot cause the outcome. So we have like two limited settings where we identify these really special populations, or we identify a special outcome, where we can use some of the tools for a causal inference to make progress with healthy worker or healthy hire bias. But ultimately, if exposure measurements are available in any capacity, be it just cumulative days on the work site, generally what you want to do to address healthy hire bias is what's often been called internal comparisons rather than external referent populations. But the internal comparisons, these are the kind of things that are subject to healthy worker survivor bias. So we by solving the problem of healthy hire bias, now we're, because of the same sort of structure, dealing with healthy worker survivor bias. One thing that comes up a lot is sort of this fear of, if you've got healthy worker survivor bias, so if you're observing that mortality is associated with whether or not you stay at the job site, I think there's this sort of reactionary view that you have to do something fancy. That's not necessarily always the case. If exposure does not impact employment, you can use standard regression methods. But ultimately, I think where the literature sort of gone out of this is using what are called G methods. So G methods are things that are valid in this setting where you have exposure affecting employment, or you have potential for collider stratification bias. But it's also valid in the setting where you just have confounding and you just want to adjust for that. G methods include G estimation, G formula, G computation. Those are two completely distinct things. Jamie Robbins has expressed regret in naming them so similarly, but just to say that those are two distinct things. And then inverse probability weighting, generally with marginal structural models, is sort of this first method. So this is where the causal inference methods really become useful, and this will not be a treatise on those. One thing to note is that occupational epidemiologists, I think, end up doing things that are very hard. And when I say that, looking at this example of G computation or G formula, just looking at the literature broadly, there's, looking at PubMed, 1,200 results, 1,300 results on this method, restricted to occupational settings, 16 results. Now this seems small, but it's not a huge field, and that's part of it. And the context for this is that If you look at G estimation, which is another, I think, very difficult method, actually the occupational literature comprises about 10% of the usage of that particular method. But then if you look at inverse probability weighting, so this is the method that I would say like sort of kicked off a causal revolution, 17,000 results in PubMed. Just looking at this, 5 results in the occupational setting. So when I look at this to me says like, oh, we're missing out on a tool that everybody seems to use and enjoy and make a lot of progress in other literatures with. So why don't we do that? Compared with other G methods, inverse probability weighting, simpler, less computationally demanding, reduces modeling assumptions, conceptually clearer, it's easier to interpret. But this is one of the things that Jamie Robbins warned us against back in 2000. And I'm gonna mostly just pause the rest of this here because the rest of it is a worked example of using inverse probability weighting. I will just say that the original statement by Jamie Robbins was that inverse probability weighting vis-a-vis marginal structural models should not be used in occupational cohort studies. But with sort of recent methods, we've been able to relax that. So again, you are more than welcome to go through this, but this is really sort of oriented towards students. The sort of take home for this, the results of this analysis were that there is evidence for healthy worker survivor bias. There's evidence that employment causes the outcome, and this is in a simulated cohort that you can actually use. So it's not a terribly interesting result, but it demonstrates that actually when there are these sort of factors, using the traditional analysis doesn't work, but using something more advanced like inverse probability weighting does. I will just say the main thing that I would like to emphasize for thinking about making progress on this in terms of like what you need to measure, what you need to think about, is understanding the structure. So understanding the things that are sort of associated with health status. And I think this is going to be maybe most relevant to you is thinking about what are the things, that maybe we wouldn't normally think of adjusting for, but really that are markers of health that may give us some way forward in analytically addressing bias. So I will just stop there for any questions, comments, but I appreciate seeing all of your faces. So thank you.